All right, ladies and gentlemen, welcome to Fighting 405, episode 9, where we go over the document number 9. This problem deals with a computer printout of some statistics based on a study, and we're interested in analyzing how these two variables, these two quantitative variables, are related. So this is a linear regression problem. We have two quantitative variables. The two quantitative variables are wind velocity in miles per hour and electricity production in amperes for one particular windmill. Now remember, when we're dealing with this, we need to figure out what is the explanatory variable, or the x variable, and what is the response variable, or the y variable. And in this case, maybe it's not immediately obvious, but if you remember, when we're given this information in the table, in the computer readout, this wind velocity implies that wind velocity itself is the explanatory variable, and we're using wind velocity to predict electricity production of this windmill. So anyway, that's that. I just want to sort of say, side note, since the AP is going to focus on not too many like calculator type problems, I really expect that you will be given some kind of table or some kind of computer readout like this. It may not necessarily be a linear regression sort of situation, but I do expect that you'll see some kind of table of information. And so I just want to stress how important it is that you understand notation and you understand how to read these types of tables. Okay, that being said, let's move on. Part A says, use the computer output above to determine the equation of the LSRL, identify all variables. So we've done problems like this. It's been a while, but we have done many problems like this. So remember, anytime you're stating an LSRL, I stressed that you should define the variables and then write the equation. So our x variable is going to be wind velocity, or observed wind velocity, miles per hour. And then since we're trying to create a predictor equation, like a model that predicts, electricity production, I'm going to define y hat. And I'm going to say that y hat is the predicted electricity production in amperes. So, my equation is going to be y hat equals, remember, wind velocity, that's your x value. And the way we read this table, the coefficient of the x value is 0.240x. And then we have the constant coefficient, which is 0.137. Okay, and there you have it. That is your least squares regression line equation based on the information in this table. Part B. How much electricity would the windmill be expected to produce on a day? How much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when the wind velocity is 15 miles per hour? So this problem is pretty simple. We just need to take our LSRL and evaluate it at x equals 25. Do the same thing, evaluate at x equals 15. And compare the two numbers. So we have 0.240 times 25 plus 0.137. And so when the wind speed is 25 miles per hour, there's a predicted amp level of 6.137. Oops. And I know it sounds annoying, but it is important that you state these units as predicted amps because that's exactly what they are. All right, and the other one, 0.24 times 15 plus 0.137, enter 3.737. Okay, well, we're not done yet because the question asks how much more electricity would the windmill be expected to produce? So we would say that the windmill would be expected to produce 2.4 amps or 2.4 more amps on a day with 25 mile per hour winds versus 15 mile per hour. Okay, and there we have it. That answers question B. What proportion of the variation in electricity production is explained by its linear relationship with wind velocity? Hopefully, while you read this, you recognize that this is exactly the definition of the number r squared. All right, so simply put, to answer this question, we need to identify r squared. Please do not pay attention to r squared adjusted. This is not the number we'll be using. Okay, we take our r squared, we have 0.873, and we would say 87.3% of the variation in amps is explained by its linear relationship with wind speed or wind velocity. Okay, and that would do it. Now, obviously, if this were a different year, we would go on and attempt problem D, but problem D asks for statistically convincing evidence that the electricity production by windmill is related to wind velocity. Now, this hopefully to you sounds like not a confidence interval. Hopefully to you it sounds like a hypothesis test, which is exactly what it is. And some of you picked up that there's a p-value column here. So, you know, hopefully you get a hint for how you might approach this problem. But the thing is, this is referring to something called the linear regression t-test, which is why I omitted part D, because for our purposes for this year, we do not need to know this. We will discuss it after the AP, but for right now, we don't need to know how to answer a question like that, although I'm sure some of you probably could. In fact, I'm sure many of you could if you really took the time to think about it. By the way, just a little insight. This is, of course, p-value. The top one is for if you're running a hypothesis test dealing with the constant, which very rarely actually happens. The second p-value is if you're running a hypothesis dealing with the relationship between wind speed, wind velocity, and amps, which is typically what we're interested in. This column here, T, hopefully you understand, that represents the test statistic. So this is actually like the t-score of our observed constant and our observed slope. All right, so anyway, as we know, though, for now, for our purposes, really, this is the only column you need to know here. You should know R squared, and you should know that in order to get R from R squared, you just radical that number. Pay attention, though, to whether R should be positive or negative. All right, that's one thing that a decent number of you missed on the mid-year. You calculated a value for R, but you forgot to put that negative there. So don't forget that. And how do we determine positive or negative? Well, look at the coefficient of the slope. If the slope coefficient is negative, then that means R would be negative. If the slope coefficient is positive, then that means R would be positive. All right, ladies and gentlemen, that is all. Take care.